Good morning or afternoon or evening, depending when you're watching this show or movie. Today we'll be going over infinite limits from the calculus text by Larson and Edwards. This guided notebook was created by Shannon, Gracey, and Beth Powell from Maricosta College. And the accompanying guided notebook here is available on www.mathcheck.net if you're interested. Alrighty, let's get warmed up here by evaluating the following limits analytically. So pause the movie and see how you do. Go for it. Okay, let's see how you did. Using direct substitution, when we plug in x is 0, do you see that we get 0 over 0, which means what? Good, more work, indeterminate. So, the more work we do is what? It starts with an A. It's not a bad word. Good, algebra. Okay, so if we get a common denominator, we need to multiply the first guy by 4 over 4 and the second one by x plus 4 over x plus 4. And simplifying and keeping our limit notation on. Remember, you can only take it off when? Good, when you directly substitute values or use a special limit. So here we go. We will get 4 minus x plus 4, that quantity, all over 4 times quantity x plus 4, and I'm going to multiply by the reciprocal of that denominator. How are we doing so far? Awesome, I knew you could do it. And now we will have the limit as x approaches 0 of, good. Do you see the 4's will zero out and we'll end up with a negative x over 4 times quantity x plus 4 times 1 over x. Those x's will divide out. And we will have the limit as x approaches 0 of negative 1 over 4 times x plus 4. And directly substituting x is 0, we will have negative 1 over 4 times 0 plus 4. So x was approaching 0, so I plugged that in there. And at the end of the day, we're left with, good, negative 1/16. How'd you do? Fabulous. All right, so now let's move on to this guy. Again, trying direct substitution. What happens? We would get tangent at 0, that quantity squared, over 0, which is 0 over 0, which means, great, indeterminate, more work. So now we'll come over here and we'll have our limit as theta approaches 0 of. So we'll have tangent theta, the quantity squared, over theta, which is equal to the limit as theta approaches 0 of. Good. We can call this sine theta over cosine theta, the quantity squared, times the reciprocal of theta, which is 1 over theta. Okay, so far? Awesome. This will give us, now remember that one groovy special trig limit? Great. Do you see that we have that? So why don't we pull a factor of sine theta apart and put that over theta, because this is all multiplication, so it's all commutative. And then we would have a sine theta over cosine theta squared remaining. And recalling that the limit of a product is the product of the limits, we will have the limit as theta approaches 0 of sine theta over theta times the limit as theta approaches 0 of sine theta over cosine theta, the quantity squared, which will give us good 1. So this whole deal here has an output of 1 by that special trig limit. So we did not directly substitute in that one. We used a special trig limit. So this guy was from a special trig limit. Now the other one we'll get by directly substituting. So we'll have sine at 0 over cosine at 0, the quantity squared, which will give us good 0 over 1, which is 0. So we would end up with 1 from that first special trig limit times 0 over 1 squared, which is 0. So this guy was found by direct sub. Cool so far? Awesome. Alrighty. So next up, we have this guy over here. So again, we're going to utilize that special trig limit. And as long as we can get this denominator to match this angle, we can utilize that. But what we're going to need to do is divide, actually it's multiplying by 1/2 over 1/2. Do you see that? Let me rewrite it so it's a little easier to see. Do you guys see over, we'll just put over here, direct substitution yields 0 over 0. So here, if we basically do this, it'll look a little funny, but if we basically multiply by 1/2 over 1/2, and then we have this limit as t approaches 0 of sine at t over 2 over t. This is going to give us, now the 1/2 that's in the denominator, we're going to pull into the limit, and we'll leave the other one outside. So we'll have 1/2 times the limit as t approaches 0 of sine at t over 2 divided by t over 2. That's the 1/2 times t is t over 2. Now by that special trig limit, we'll get 1/2 times, good, 1, which at the end of the day gives us a result of 1/2. Good so far? Awesome. So this here, this whole limit by the special trig limit was 1. And over here, when I did this 1/2 times t is where I got this t over 2. All right, so let's move on to the lesson today. More limits, as you may guess. So here we go. This deals with infinite limits. So here's a definition of infinite limits. We're not going to go too far into this. If you take calculus in your upper division math, you'll go way more into depth with the epsilon delta proofs. But basically, the big picture idea is if you get a result of positive infinity, right, we're going to focus on positive infinity. That's what I think I have the illustration for. So basically, if you look at this visual as your function from both the left and the right side of C right here goes up to positive infinity. And here's the delta here. So this right here would be c minus delta, and this would be c plus delta. And what this is saying is, hey, you take some arbitrary y value m, right? That's over here. You're always going to get higher than m because your graph is increasing without bound. And you can show a similar visual if you're going down to negative infinity as well. You could really just flip this visual. So basically here you can get, if you're looking at infinite limits, it's very useful because what happens is this gives us the behavior of the graph at vertical asymptotes, and for curve sketching is very, very useful. So on our first exam, I'll be very clear as to when you can or cannot, put a result of infinity or minus infinity down when doing a limit. Technically, it doesn't really exist, right? But we want you to be able to ascertain when a limit is infinite and which direction it goes. Does it go up or down? Okay, so here we go. There's different ways to determine infinite limits, graphing, tables, all that kind of stuff. The first exam, we're not going to be using calculators, so there are some ways a person can do this. You can plug in small values values that are very, very close to what the domain value you are approaching. So I'll show you this first one using that method. And then what ends up happening is you end up either going to positive or negative infinity if you are examining what's happening at a vertical asymptote. So if you notice here, as x approaches -3, you will be at a vertical asymptote. So let's just check it out. What are some numbers, that are really close to -3, but from that left side? Good. Why don't we just look at trying? I'll do some side work, right? And why don't we just try plugging in x equal to -3.1. How about that? And you can use a scientific calculator on the exam, meaning you can do these simple computations. So if we did that, we would get -3.1 divided by -3.1 squared minus 9. This would be -3.1 over -3.1 squared, using just a real simple calculator. I've got mine handy right here. Let's see what we've got going on. So I got this is 9.61 minus 9. So basically what's going to happen is you have that negative in the numerator, and you're going to get a very small positive in the denominator, 0.61, which is the same as -3.1 over 61 over 100. And if you kind of simplify that out, you'd be multiplying by 100. So do you see you would end up getting -310 over 61. So what that suggests is this. It suggests that this guy is going to negative infinity. All right, let's look at a picture of what that graph would look like. So we'd have, it was, I believe, x divided by quantity x squared minus 9. and we're interested, we'll just go to the Zoom standard. And actually, yeah, we're good here. So let me go ahead and copy this graph. Oops. And as you can see, if you take your little hand over here and you approach -3, here's x is -1, 2, 3. You approach -3 from the left. So you go down to negative infinity. So we verified that on the graph. And we're just kind of going down, 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 down. Groovy? All right. So again, one way is graphing it by hand. This one's a little harder to graph by hand. We'll be developing skills for that as we go through the course. But in this case, you can just really substitute a value. You know that when you have a vertical asymptote in the picture of your graph, you're either going to go up to a positive infinity or down to negative infinity. So really, once you ascertain the sign of what's happening as you're approaching the domain value where the vertical asymptote occurs, you know if you're going to infinity or negative infinity. So let's try the next one. Let's try direct substitution and see what we get. This would give us secant at pi times 3 over 6, which is secant at pi over 2, which is undefined, right? We have a vertical asymptote there. So a graph is useful in something like when you're working with something like this. And I usually typically just always do the graphs for the sine and the cosine function, and then I get their reciprocal functions from there. So let's check out what the picture of our graph would be. So I'm doing the scale like this because if you recall, the period is going to be 2 pi, which is the period of the secant function, divided by the coefficient to the x. So that ends up giving us 12. So this graph will complete its one period of its graph in 12 units there. So now, looking at some values, if I kind of dash in this cosine graph, do you see that at 0, if I plug in 0, I'll have cosine at 0, which is 1. So again, I'm considering I'm going to have this green graph is going to be cosine at pi x over 6 is this green graph, and then I'll dash that in. So if I plug in 0, I'm going to get an output of 1. And then if I plug in 12, do you see that it'll be back at 2 pi? Good. So that'll finish it off. So that's 12 is going to be, I doubled this, so 2, 4, 6, 8, 10, 12. This is going to be where the cycle will end for this first one. And then halfway in between would be 6, right? And cosine at 6 pi over 6 would be cosine at pi, which is, -1. And that's halfway in between. So what will happen is, and then the zeros will be at in between there, right? which would be when x is 3 and when x is 9. So that would be here and here. So our dashed in graph for our cosine are here. So now you make vertical asymptotes wherever where the zeros of the graph are. So we get our zeros here, which is actually the input value of interest, right? We'll get our zeros here. And then if you recall, you make parabolas, oops, that's no good. Parabolas opening upward at the maximums and downward at the minimums. So now let's see what happens. So I just did kind of a snapshot of this graph. So as we approach graphically now, as we're approaching 3 from the right side, right? So x is 3 is right here. So we're approaching from the right side of 3. Do you see we're going to, good, negative infinity. Perfect. So therefore, what we found was the limit as x approaches 3 from the right side of secant at pi x over 6 is negative infinity. That's our infinite limit. And again, we were approaching from that right side. So you go down to negative infinity. All right? How'd you do? Awesome. Okay, so now we get to the official definition of a vertical asymptote. So if f of x approaches infinity or negative infinity as x approaches c from the right or left, then the line x equals c is a vertical asymptote of the graph of f. So now we have a theorem for vertical asymptotes. So this theorem basically, specifies that f and g are continuous on this open interval containing c if your function doesn't zero out at x equals c, and if g at c is 0. So what this means is you do not get an indeterminate result. You get some sort of value constant over 0. Okay. And then there also has to be an open interval containing c such that that function in the denominator is not always 0. If that's true, then you get a vertical asymptote at x equals c. So you can tell by the limit, the format of the end result of the limit if you're going to get a vertical asymptote, which is pretty awesome. So here we go. Now, if we were to look at that last one, by the way, so if we were to consider this last problem that we did, and if we had broken this up as, or actually, let's just do a kind of a general one. I mean, consider that if we had the limit as x approaches pi over 2 from the right side, okay, of secant at x, we could rewrite this as the limit as x approaches pi over 2 from the right side of 1 over cosine at x using the reciprocal identity. But plugging that in, that would give us 1 over cosine at pi over 2, wouldn't it? Which is 1 over 0. So that would tell us, hey, we're going to have a vertical asymptote at x equals pi over 2. Make sense? All right, so just a little kind of a side note there. So now let's take a look. Let's find the vertical asymptotes, if any, of the graph of the function. So if we look at this guy here, what do you think? Cosine theta over theta. Cosine theta over theta. So what would you say about that? Good. At theta equal to 0, do you see there's a vertical asymptote? Potentially. But what else would we want to think about? We don't want to have, an indeterminate format. So what is cosine at 0? Good. Cosine at 0 is 1. So we're safe there. And do you see that would be the only vertical asymptote on that graph? So we'd have this guy right here, theta equals 0 is a vertical asymptote. Let's see what that graph looks like. So if we go back to our y equals, and let's put our window really close to 0. So we'll do negative 2 to 2, I guess. And then we can do here, over here we can do, for the y, we can do, we'll also just do negative 2 to 2. And let's see what we get. And as you see, we have that vertical asymptote at x is 0. And if we pull that graph out a little bit, let's go to zoom out and see what it looks like. You can see it's got kind of a cool little curve right there. So let's get a picture of that one. And paste it here. Okay? Good so far? And here's our vertical asymptote right here at theta is 0. In this case, we did it as x and y. Now, do you see how these kind of dance around the y-axis? So we're going to learn the infinite behavior of graphs. In other words, horizontal asymptotes when we get into, I think it's section 3.5. And we'll learn about curvature and all kinds of cool stuff in chapter 3. So stay tuned for that. All right, so why don't you take a look at these guys and see what you think. So for this one, I mean, what do you think we could do with this? Good. Why don't we factor this, right? And see if we can divide any common factors out. So we'd get x plus 2 times x minus 2 over, again, factoring by grouping, we can factor out an x squared from the first two terms of the denominator, and we'll get an x plus 2, and then a plus 1 times x plus 2. And then we'll get h at x is x plus 2 times x minus 2 all over. X plus 2 is the common binomial factor times x squared plus 1. So I just factored out this common binomial factor here. And then it looks to me like we can certainly divide out an x plus 2. And we can say, okay, h of x is equal to x minus 2 over x squared plus 1 as long as x is not equal to, very good, negative 2. So what does that negative 2 represent? Beautiful. It's a hole in the graph because we were able to divide it out, right? So at x equals negative 2, there's a hole in the graph. Now, is x squared plus 1 ever equal to 0? That would be the only other problem child. This guy can't equal 0. So if you continued to solve, do you see you would get x squared can't be -1? But isn't that imaginary, right? So there is no other way that the denominator can be equal to 0. So we have no vertical asymptotes. We just have a hole in the graph when x is -2. Okay? All right. So moving right along, properties of infinite limits. So let's suppose that you've got this limit as x approaches c of this function f at x, and it has an infinite result. And another limit has a finite result. You get 3 or -12 or 22 thirds or something like that for the as g, the limit as x approaches c of g of x ends up being finite, right? Some constant. So it turns out that, if you're infinity, remember, is just an idea. So if you're adding or subtracting a number from infinity, you still get infinity. If you're multiplying a positive number to infinity, you get infinity. And if you are dividing by infinity, and this works for negative infinity as well, you get 0 as long as you have a constant in the numerator. All right. So again, similar properties hold for one-sided limits and for functions in which the limit of the function as x approaches c is negative infinity. You'll learn more about indeterminate forms when you're in Calc 2. There's some more indeterminate forms that you'll be working with. So here we go. In this case, the limit as x approaches c of our function f is a constant, -2/3. And the limit as x approaches c of g of x is the infinite limit, infinity, positive infinity. And then we have another limit as x approaches c of h of x is 5. So we're going to determine these limits. So let's check it out. We're going to use our properties of limits. So remember that this is going to be equivalent to the limit as x approaches c of f at x divided by the limit as x approaches c of g of x, because the limit of a quotient is the quotient of the limits. But what were those values? Good. The numerator takes on a value of -2/3 and the denominator takes on a value of infinity, right? But that's not a real proper way to write it. So basically, this has an output of this. This guy has an output of this, but we don't want to write it like that because we were told that this has a result of beautiful 0. Okay. Perfect. So now let's do the next one. So here, this is going to be equivalent to the limit as x approaches c of f of x minus the limit as x approaches c of g at x. And that whole thing will be squared. So I brought the limit notation into that most outside function of the composition. So a lot going on with this one. And what was the limit as x approaches c of f of x? Remember, it was -2/3. Good. So that was what this one is. And then this guy is minus infinity, right? That's what we had gotten for the other one. And then what are we doing with the results? Whoops. We're going to be squaring it. So here, do you see you would have had a negative minus infinity would give us good negative infinity, but we're squaring that, so we'll end up with perfect positive infinity. All right. Now this guy will be equal to, I'll go ahead and bring that 1/3 outside of the limit. And then we'll be getting the limit as x approaches c of h at x times the limit as x approaches c of f at x. And let's see what those were again. For the h of x, it was 5, and for the f of x, it was negative 2/3. So these are our equivalences. And I got all that information from the beginning of the problem. So we'll end up with, let's see, I believe we get, at the end of the day, we get negative 10/9. Okay? All righty. Well, that wraps it up for today. We'll be starting chapter 2 next time. So have a fabulous weekend. Bye.